problem 3 here. So problem 3 is like kind of like digit DP, you could call it. It's not really standard digit DP, but it's kind of like doing those digit stuff, which is not that common in USACO, even in the whole history. So it's probably a new type of problem that we need to pay attention to. So essentially, you're given like n digits. Each of them is AI. So essentially, a range of a list of digits, and then you're given A and B here, and then you want to find. So you will answer Q queries. Each of them is L, I, and RI. Essentially, they're asking you to solve the problem in a certain range of digits. Essentially, in each query, you kind of want to go from left list and to the right list, and each time you have a pile that it's not exact pile, but it's probably you're building the numbers that you want here, and then you can build either each time you visit a new digit, you can either put it in the front of the number that so suppose this is the number you have built so far. You can either put in the front or in the back, or you can kind of like ignore that digit and then go to the next one. So if you keep visiting digits, and then you kind of like keep adding them forward or backward to the thing. So there, as you can see, there are 3 RI minus LI plus 1 different possible way to add those digits, because for each digit you kind of have 3 different possible actions. Yeah, so they're asking you like what is the number of ways so that you can build an integer that is between this range. So the range is kind of fixed, right? The only thing changing in each query is the range of the digit that you can choose. So it's, yeah, there's a lot of components going on in this problem. So we try to like simplify this a little bit. So this problem asks us to actually find the amount of way to make an integer that is falling to this range. This very, very common trick of doing this problem from A to B is that you could kind of like count the way to, so suppose we want to solve something like this, right? Essentially, what you can do is kind of like, suppose you are solving the number of ways to achieve this, you can kind of like having the number of ways to achieve this, and then you subtract it by the number of ways to achieve this, right? So the way to put the problem into this way is like, you got one less constraint to care about, right? You only care about you need to be small or equal to some number, and this is a really good thing, right? So yeah, so let's start from here, because once you know how to solve this, you kind of have already the way to solve this by solving 2 instances of the solve function here, right? So let's just assume that we just want to solve some problem with only a upper bound. So a way to put this is like so let's forget about queries. Queries is probably too complicated for this. Essentially, suppose we're given the list of digits. We essentially we assume Q is equals to 1 here. Then we have a list of digits, and then we want to add them one by one so that we're trying to build an integer that is smaller or equal to b, right? So let's see how we should actually build this thing, right? So essentially, for example, there are 2, 3, 1, 4, 5. Those are the digits, and then the number that we want to put is probably like 3 to probably 211, something like this. So suppose we're gonna put 2 here. So essentially, what you can do here is like when you are assigning, you can kind of assign which digit. So suppose we put our first digit in some place. I'm gonna have a longer number here. Suppose so this is b equals to this, and then so we kind of like designate our first integer or first digit to some certain location. Say I'm gonna insert this 2, and then in the end of the number, I'm gonna fix it to be in this place. So the good thing about this way of thinking is like after this, when I add new integer, their location is also fixed. For example, I put 3 here, then it'll be third digit of the number in the end, right? So if I'm gonna put them in the end, then it'll be the 5th digit and put it here. The good thing is that like the location of the digit will be fixed once I fix the first location. So what I'm gonna do is so I can index it by 1, 2, 3, 4, 5, 6, 7, 6 here, and I'm gonna do a DP here where essentially DP LR. So L here we'll make it 0 first. So essentially, then R is the current digit that I'm adding, right? So suppose I'm starting from 0 here. So 0 here, we just ignore it. Suppose this is not the part of state. R is the current digit that I'm visiting, that I'm going to choose whether to add in front or add to back or discard. So and another 2 thing that I want to keep track of is like the left bound of the digit and then the right bound of the digit, the index of the digit that I have. So I have choose so far, right? So I'm gonna record a DL, so digit L, digit R, which is essentially the current front and end of the digit that I have confirmed so far, right? So as you can see, each time when I'm visiting this edge, this state, I can kind of like transit into kind of like DP R plus 1. So R plus 1 is the next digit I'm gonna decide, and I'm gonna either put it to the front or put it into the back, or I'm probably gonna not do anything and discard this number so the range doesn't change, right? So this is probably the number of ways to actually build the numbers like this. The only thing left in this formulation is like I somehow need to keep track this nasty thing where I want to build a number that is smaller or equal to b. So this thing is kind of like really weird to actually keep, right? So let me kind of like offer some intuition here, right? So it turns out that it's really important to actually know. I will copy the number here. 2, 3, 4, 5, 1, 3, 4. It seems to be very important to actually keep track of the number that you built so far, like regarding the relation of the corresponding segment in the original number. So suppose, let's say, we have a 5, 4, 1, 5 already built here, right? Then once we are trying to choose the number here, or let's ignore the 2 here. Suppose we're going to choose the first digit here, because this segment is larger than this, right? We're going to end up, we will need to choose a number that is strictly smaller than 3 here, right? Because only in those cases, 1 or 2, or probably 0, you will be able to have the whole number that is smaller than this, right? And on the other hand, for example, if you have something like this, you have chosen all the things like this, and it's something like this. And when you're choosing the last digit, you can add arbitrary anything here, right? Essentially, literally anything here, because this number is already smaller than this number. So no matter what you add, all the things will fall into range. Or on the other case, like they're exactly the same here, then adding the last one, you can only choose 1, 2, 3, 4, right? You cannot choose anything larger than 4 because you can kind of like want your final number to be smaller or equal to this. So this gives us the intuition like how important of the of whether the current segment is larger than the corresponding segment here. So this also kind of like gives us a hint of how we're going to design our DP transition, because so suppose you are at a state where, so let's kind of represent this relation by another location where this is either smaller or equal or larger. So let's say if we want to add something in the front, right? We want it to be, so suppose we are at DP R DLDR smaller than, right? And then we decide to, okay, we're going to put something in here, right? Which, and because this is probably smaller, for example, this is 3415, this is smaller, then we can kind of like put things, if we want to transit to DPL -1, DPR, and want them to be smaller as well, then you need the number that you put. For example, suppose the current number is D. You want D to be smaller or equal to, like, for example, let's say B DL -1. So essentially, this is the DL -1 bit, the digit in the original B number, right? So you want this number to be smaller or equal to this number so that you can keep this like smaller than relation. Or say if you want to transit to this larger than, then you want your D to be larger or B equals to -1, right? So you can see how you could kind of infer whether adding one digit in the front will change the relation just by the relation of those two numbers and then the original relation between those two segments, right? It's like merging those two, like those one digit with one segment using those things, right? So you could figure out similar thing for adding at the back here, and I won't show it here. So essentially, you can just like do similar thing like this. So the transition will be quite similar to those. So in the end, you will have the state you will have is DPR. Let's write it again. So you have three different possible things here. So essentially, you have let me know that, okay, so we were ignoring the query like this, but it takes us to actually compute all the answers for all the query from 0, 0, 0, 1, 0, 2, essentially L equals to 0, all in once around this DP calculation. So this DP calculation will cost you n times d square, probably times 3 because you have 3 states, and then some constant of like number of transitions here, but not asymptotically is something like this, right? It costs you this complexity to actually get the DP table for all the range like this, right? Because in the end, you kind of have this like DP R0. So suppose B has like k digit, like I'll just write this, B minus 1 digit, which is the rightmost digit of the number B, and then you want it to be smaller or equal. So you kind of like sum up those two states, and then you will get final answer here for query 0 to R, right? You sum up those two options, and I have to mention that here we are building some digit, some number that is larger, that has exactly the number, the same number of bits, the same number of digits as number b, but if we're using strictly less digit than b, then we're definitely like building a valid solution, because like we have less digit, we must be smaller or equal to b. So this is for exactly b bits. B digits. And if you want to do like smaller than b bits digits, you can just do essentially you can just choose, you can sum over all the number from 1 to b minus 1. Essentially you're choosing I digits, and then you can choose your digits from any of those 2 digits. Some rough formula like this, because you can choose them, and then you can kind of like add them either in the front or back. So this is something that you can compute in the other loop or something. But essentially, yeah. So I got a question here. So DL and DR DL and DR essentially is the digits, the range of digits that you have built so far in the final representation. So each time you decide to actually put a number in the front or in the end, you're kind of like effectively extending the range. So if you're going to put a number in front, you will kind of like have like DL minus 1 and DR as your new range that you have decided. So essentially, that's how you calculate like exactly b digits for this. So once you have this, like using n times d squared to actually calculate the DP table, you automatically get this for a fixed endpoint and then arbitrary r, right? So essentially, in the end, you can kind of like try different left point. So there are totally n different points. So in the end, you will have this complexity to be able to answer any query that such that their left point is smaller than their right points, and then both of them is like between 1 and n. So this is our final complexity here, which is n squared d squared, which fits into the time here. Since n is equals to 300 and then d is 18, which is the number of digits in the number b. Yeah. Any questions, comments? Or any? Yes. So yeah, there's a good question. So I am getting from that direct message, so you probably won't see it. So essentially, how do I line up? So the question is, how do I line up the digit that I add with the digit in the B? So this is a good question. So essentially, what I'm doing here, when I add the first digit, I'm gonna fix its location in the final representation. So essentially, for the first digit, I can kind of like add it, or for the first digit that I will add them into. So for example, this is some number in B that has like as B, which has 6 digits. Adding 1 here, I can either fix it to be here, or here, or here, or here, or here. So essentially, I can choose when I add my very first digit into the representation, I can kind of like fix its location. And once I fix that location, so essentially by fixing location, I mean I can explicitly set DP 0 R 3 and smaller to be 1, because I have one way to actually put this in here, right? I have also one way to put 2 here, and those are the, probably you can solve this as a like DP based case where I kind of like fix the very first digit, the location of the very first digit that I add. And the good thing about this is that everything afterwards that I add will also have a fixed location, because I can kind of like, I'm kind of like extending my range from here. So that's how I'm gonna align with the digits in B, because I'm gonna fix the digit at the moment that I add it. Yeah, okay. So yeah, I think that's all for the size for the solution thing. So I could go back to a little bit so to like ask him more related stuff. So we're actively recruiting students to participate in our class, and also we have been forming teams to do contests like HPI. And if you have any interest in doing those stuff, even though you are not student here, or you feel free to have some consultation session with our coaches, including me. And if you are interested in forming up teams or any other things, like feel free to reach us. We might give you some assessment here. And also we have been sending a lot of students to Platinum this year, and also we have sent students to camp last year. And if you have any question, feel free to reach out to us by sending email to the to the poster that you see. So essentially info at scamp.academy. So essentially about like potentially course opportunities or consultation sessions. And that's pretty much all for today. If you have any question, feel free to unmute yourself and then ask. And otherwise, let's call it a day. And thanks everyone for attending.